Students, actually discovery of lanthanoids were started from 18th century. Few lanthanoids were discovered, but in 1914 Moseley said that there are 15 lanthanoids. He has studied X-ray spectra of all those elements. So people, what they were thinking as a separate element, within that total 15 lanthanoids were there. They were occurring together. Their chemistry is somewhat similar. It is because of their tendency to show the oxidation states is somewhat similar. Their sizes also are similar. Now our point of interest is oxidation states of lanthanoids. What is oxidation state? Oxidation state is a charge beared by element in its compound. All lanthanoids are metals. They are electropositive. Means what? They will give electrons. They will furnish electron and will obtain positive ions. You will understand the electronic configuration and possible oxidation states of lanthanoids. Let us explain this table. If you see lanthanum plus 3, what is electronic configuration for lanthanum plus 3? 4F0. Gadolinium plus 3, 4F7. Lutetium plus 3, 4F14. Europium plus 2, 4F7. Ytterbium plus 2, 4F14. Cerium plus 4, 4F0. Terbium plus 4, 4F7. Extraordinary stabilities were shown by these oxidation states for respective elements. Now, how can we explain this extraordinary stability? If you see the electronic configurations, what will you find? F0, F7 and F14 electronic configuration. F0 means vacant orbital, empty orbital. F7 means half filled F orbital. F14 means completely filled F orbital. Means if orbital is empty, if orbital is half filled or orbital is completely fulfilled, then such oxidation states govern extra stability. But by the same time, we were finding all elements exhibiting +3 oxidation state. Can we explain it on the basis of electronic configuration? Not only +3, if you see the praseodymium shows +4 oxidation state, there is no empty orbital, there is no half filled orbital, there is no completely filled orbital. Accordingly, samarium also shows +2 oxidation state. For europium we can understand, but for what about samarium? So there are many other things which we have not considered. So only electronic configuration is not a solid base to explain the oxidation states. On the basis of general chemistry, it is okay. But now, if in true sense we have to explain the oxidation states, then we need to take help of thermodynamic consideration. More negative the delta G value, more favorable the reaction it will be. Formation of oxides, formation of positive oxidation state its stability will depend on delta G value. And this delta G value depends on three factors. Number one, sublimation energy or atomization energy, conversion of metal to atomic state, metal to vapor, metal to gaseous state atom. From that isolated, separate gaseous atom, we need to remove the electron. Yes. Then the energy needed to remove the electron from separate, isolated gaseous atom is called, right, ionization energy. So first sublimation energy, second ionization energy. But once ion form, say La plus 3, what that La plus 3 will do? La plus 3 will combine with 3Cl minus to form LaCl3. Solid it will obtain, and when solid forms, energy gets released. What we say for that energy? When 1 mole of solid forms, energy liberated is called as lattice energy. So in a solid state, we will consider lattice energy. Or if solution state is there, as you put the ion in the solvent, a solvent molecule will surround the ion. And when they surround, attraction will be there between the positive ion and the negative pole of the solvent molecule. Energy liberated due to surrounding of solvent molecule, it's called as solvation energy. So what is the conclusion now? Stability of oxidation state depends upon three factors. Number one, sublimation energy. Number two, ionization energy. Number three, lattice energy or solvation energy. Combination of all those three will decide the fate of that ion, whether that oxidation state will occur or not. In addition to thermodynamic consideration, kinetic factors also are there. Rate of the reaction, speed of the reaction also affect the stability of the ion. So in true sense, if we need to attribute the reason for occurrence of particular oxidation state, thermodynamics and kinetic factors are to be considered. Okay, these lanthanoids show variable oxidation state, but no more variation, +2, +3 and +4, that much only. In case of transition series elements, right from +1 to +7, that much wide range of the oxidation states were there. But in case of inner transition series elements, in case of particularly lanthanoids, only up to +4 we can proceed. So variation is not more. It is there to the less extent. Now question arises, why it is so? If you study the electronic configuration for the various oxidation states, you will find after removal of electrons from the 6s orbital, electrons will be removed from 5d in case if they are there, or electrons will be removed from 4f orbital. Now I show you this one quantum chemistry approach for element thulium. See, in this diagram, the f orbital has less penetration. It seems that near to the nucleus, but compared to 5s and 5p, energetically it is what? Higher. As the thulium removes 3 electron and forms tripositive ion, the 4f orbital maxima, if you note, shifts towards nucleus. Somewhat more penetration is recognized compared to previous situation. 4f orbital electrons remains closer to the nucleus. Attraction remains more. So will it be easy to remove electron? No. That difficulty in the removal of electron reveals that formation of +5 or other higher oxidation states, even though n electrons are present, is difficult. It is because of change in the energetics of the ion. So I was saying repeatedly in the electronic configuration topic, electronic arrangement depends upon energetics of the various orbitals, and that changes as the situation changes, that changes as number of proton changes, that changes as number of electrons present. So removal of fifth electron becomes very tough. So ionization energy will be the very high. If ionization energy is investment, but that much return should be there. If those returns are not there, that oxidation state will not occur, or that oxidation state will not be favorable. Therefore, higher oxidation states are not observed by the lanthanoids, and answer for this can be given by quantum chemistry approach. One recent development I bring it to your notice, means it is in 1985. People have discovered the lanthanoids in +2 oxidation states in various complexes. So, as I said, +3 is a general stable oxidation state. Likewise, +2 also is a stable oxidation state shown by the lanthanoids. Lanthanoid shows close resemblance to aluminum. Lanthanoid shows close resemblance to barium. Barium dipositive, aluminum tripositive. So +2 oxidation state also we can explain on the basis of thermodynamic and kinetic considerations. In conclusion, lanthanoid show less variation in the oxidation states. Lanthanoids are reactive and forms positive oxidation state, but show +2, +3 and +4 as oxidation states. So once we know now oxidation states of lanthanoids, students, let us discuss magnetic properties of those lanthanoids. One of the important point from application orientation point of view. We will discuss in the next part.